It's really my pleasure to introduce Fan Li. I know Fan for a very long time. Fan is a professor of statistical sciences and professor of biostatistics and bioinformatics at Duke University. She started her career at Duke in 2008. She got her PhD from Johns Hopkins, Bloomberg School of Public Health. Fan and I overlapped when she was a PhD student, and I was a very, very, very young junior faculty.
And I learned Bayesian statistics from you.
No,
I took your class.
Did you?
Yeah.
Oh, I didn't know that.
Yeah,
around
great. 2003.
Really? Oh my God! Don't say that. So yeah, I was teaching to Bayesian statistics when I was just only 16 years old. But anyway, so she was then a PhD student at Johns Hopkins with Konstantin Frangakis, and I don't know how many of you know about Konstantin. Konstantin was a PhD student of Don Rubin, and he developed the foundational idea of principal stratification. I was thinking principal stratification. So anyway, so although Fan Li is at Duke, I think she also got some of the causal inference learning from this part of the world. So I'm just gonna stop here and give the audience to you, Fan Li, and she's gonna have a tutorial for a couple of hours. So we will have a break in the middle, and so hope you will enjoy. Thank you, Fan, for coming.
Thanks, Francesca. Well, thanks everyone for coming. So this is mostly based on a review paper I wrote, published last year on the Royal Philosophical Transaction of the Royal Society. And then recently I found some out of Newton, Isaac Newton also publishing Philosophical Transaction, so I all of a sudden feel, wow, this is pretty cool. Anyway, so this is the, so first of all, I want to ask the audience, I assume most of you have a little bit knowledge about causal inference, or, okay, I see a happy nodding. And also, I assume most of you know a little bit about Bayesian. Okay, so great. So then I can quickly go through the first part. Because today, I was working on causal inference for a long time, and also, as you just heard, I took my first Bayesian class in 2003 from Francesca at Johns Hopkins. Then I went to Duke. Duke is a very strong hold in Bayesian statistics. So then I started to ask myself, okay, so Bayesian and causal inference, when you combine the two, what is special? So then that motivated, when I wrote this review, I don't want to just I don't want to just give a catalog of what has been done when people are doing Bayesian and causal inference. I want to see that what is special about combining these two. And so that will be the main theme of today's tutorial. Okay, just a very, very quick summary, because most people know causal inference, so I just quickly talk about what, in my view, what is causal inference about. So we all know statistics infers association between variables, okay? And then probably lesson one in any elementary statistics class is association does not imply causation, okay? So then this seemed to be, okay, then what are we doing here? Well, turn out that we'll call it statistical causal inference. It's mostly about building a framework. So this framework first, it defines what is a causal effect, using those variables and using some concepts. And then the second is, once you define this framework, what you need to specify some assumptions under which you can identify causation from association. Remember, just without any assumption, you cannot say association is causation. But we cannot stop there. So causal inference is about give you a framework. Once you define what is causal effect, you can specify assumptions such that you can identify causation from association. And then, of course, whenever we have assumptions, it can be violated. So then the third component to me is to assess the sensitivity within this framework to the violation of those key assumptions. So this is statistical causal inference is about. So then there are several frameworks to this, and then traditionally structural equation models and DAG, the Bayesian network, and then I would argue the primary framework now used at least in statistics and medicine, in social science or econ, is the potential outcome framework, or the so-called counterfactual framework that was first conceived by Neyman over 100 years ago, and then advocated by, then pushed forward by Rubin in the 70s. Okay, so just overall, so what is this framework about is, there are many causal problems, but this framework is to evaluate, so it is centered on this thing, on this goal, is try to evaluate the effect of a treatment or intervention, which is cause. Basically, the cause is specified here on the outcome. Okay, so you have a cause, you have a treatment or intervention, and then you have outcome. You want to evaluate the effect of that cause on outcome. So it's a very focused task. It turned out that even that is not easy. Okay, so the main challenge of this is, of course, confounding. So there are factors that affect both the treatment and the outcome, and those are the hard part. So that, again, that's a very quick run over of things. So then I'll get into the the Bayesian part or the framework quickly now. So we need some setup and notation. So assume we have data. So this data is a simple random. So it's a random sample of n units from a population. The concept of population called inference is very important. What is your target population? Because we have a sample. We have a sample drawn from target population. We can do inference on the sample, but we really want to make conclusions to the target population. So the sample and population are different. They are, of course, if you have simple random sample, they're the same. But often that's that can be different. So I will leave that for another day, but just keep that in mind. So then we have, let's say we have a treatment. Again, to make life easy, let's assume the treatment is only binary. Then for each unit, we observe the treatment status, we denote by Z. At Harvard, especially biostatistics, people like to use A. But here I use Z. In the Harvard, on the other side of Charles River, people use Z. The stat department use Z. So covariates, I say X, and the outcome Y. Okay, so those are all observed. And then what is potential outcome is for each unit, there are two potential outcomes, Y1 and Y0. Of course, when I say each unit have two potential outcomes, I already implicitly assume there's the so-called stable unit, the pseudo assumption. Basically say there's no interference and also no different version of a treatment. Those are all pretty standard. And then from now on, I will use bold to denote the vector of those, like this variable to denote the whole data of the sample. Okay, this is all standard. And then, so we need to define causal effects. So that's called causal estimand. Those are basically the quantities that defined in causal by potential outcome or counterfactual. Those are called counterfactuals, okay, because you don't always observe both. And so then we have a bunch of estimands that define on the potential outcomes. Those are the standard ones. So they can be individual treatment effect. Basically, for the same person, had I been able to assign this person to treatment versus control, then what the outcome would be. So I usually use a Greek letter tau to denote the treatment effect. And then this correspondingly is there's something called conditional average treatment effect, or CATE. It's the treatment effect. It's a treatment effect of the units that have the same covariate value x. So that is CATE, and it can be different across different x. And then for a very long time, people talk about average treatment effect, the PATE. So population average treatment effect or average treatment effect, ATE. That's just this CATE or this ITE. You can think of this as an average over a target population. So it's expectation. And here I didn't write is the over a population. Okay. So this is kind of there are many other estimates, especially if you, for example, if you are in biostat, survival outcome is, time to event outcome is common, and then you have other things, and the binary, you will have ratio, but you get the idea, okay? So we all know that fundamental problem of causal inference is, well, it's great, all this definition, because you're comparing the same person on the two counterfactual conditions. So it sounds pretty reasonable. I would claim that this is pretty reasonable. But then the question is well, this fundamental problem of causal inference is, well, you've only got observe one of the two. So you observe the potential outcome corresponding to the actual so the actual treatment corresponding to the actual treatment, like the outcome that corresponding to actual treatment. So mathematically you can define you can write this. So I usually denote the observed outcome as yi, just y. Sometimes I use y-obs to emphasize this is observed, and the other one is missing. Okay. So once you look at this, you realize, oh well, so at least half of the data are missing. All right, half of the data missing in any data, like because the causal estimands is defined as the contrast of potential outcomes. Actually, you observe only one of them. So essentially, causal inference, you can view it as a missing data problem. But this is not like whatever missing data problem. This is clearly a structural, the missing data is very structured. So if you know a little bit history about the causal inference and the missing data, you know that these two things are very closely connected. And Darubin in the 70s, so in the 74, if you see here, in the 74 paper, 78, around that time he was working on causal inference. But you probably also remember missing data has the most classic paper is 76 paper, biometrical paper on missing data. And so that is not a coincidence. We realized the connection between the two because, and actually the 78 paper, interestingly, the 74 paper is giving the idea. 78 paper, Anos paper, is actually about Bayesian inference of causal effect. It just for the longest time, then people actually stopped working on Bayesian. But originally, this was all connected. It's because this is, you can view this whole problem as a missing data problem. Okay, well, it's almost in the sense that you're missing half of the data. So the simplest thing you can think of is, well, I'm going to impute. If somehow I can, from the observed data, to impute the missing data, I can do causal inference, right? So, well, you can do that, but you need more assumptions. So then so we need more assumptions. So we can have structural assumptions or stochastic modeling assumptions. Again, so another quick review is, so in the assumptions, and the majority of the causal study assume versions of ignorable assignment or ignorability. So that's just consists of two sub-assumptions. The first is the unconfoundedness assumption, or it's selection on observables or no unmeasured confounding. So there are many names. So essentially this says that every unit, say, treatment assignment only conditional on the observed x. Only conditional on the observed x. So it essentially say that there's no unmeasured confounders. Okay, so this is an untestable assumption, but a lot of work assume that. And second is the overlap assumption, or also known as a positivity assumption. Just say that every unit, the probability of being assigned to treatment or control is bounded away from 0 and 1. So this is testable, so people take it for granted. And it turned out that this is actually ultra important in causal inference, that it's become more prominent in recent years. And then anyway, so once you have the unconfoundedness assumption, the nice thing is then you can get rid of those two conditions. Then you can just, we usually denote the propensity score by E. It's just the probability of being assigned to treatment given X. So this is called the propensity score. And this thing plays a central role in causal inference. Actually, it becomes clear later. Also in the Bayesian approach, this is also important. A little bit, almost like a paradox, but I will get to that. So this is a very quick view of things, right? So now, once you have those assumptions, so that, yes?
Okay, to ask a question?
Yes, sure.
Fan, I want to ask you, you know this SUDFA, I don't know if you're getting to the SUDFA assumption?
I'm actually not going to get into for this tutorial, no.
Could I ask a question?
Yeah, sure.
So I was wondering, how does the exchangeability, the Di-Finetti's exchangeability relate? Does it relate at all to SUDFA? How does it relate to causal inference?
I actually, you're getting, so it's actually related here. I actually get rid of the Di-Finetti because I feel it's complicated. So, yeah. So I don't think it's related to SUDFA, but it's very important when we start to talk about, when we talk about later when I build a model for things, and then I have a parameter, and I say that exists a prior. So it is related, but I don't think it's related for pseudo.
Okay.
Yeah, it's related to actually the fact that you can rewrite the joint distribution in the product of those individuals. But that's actually an important point. I was earlier when I wrote things, I always put the definity, but then I realized I can just assume something weaker is just conditional independence. But that's too technical. Okay, okay. So let's go back. Oh, okay, yeah. Go back to this. So now I have those assumptions. So then once I have some assumptions, so remember, causal effect is about the potential outcome. What do you want to, causal effect is defined on potential outcome. But what we do have is observed outcome, right? So we want to connect the two. So what do we do is, well, why we can do this is because under ignorability, then we can actually prove that, this is actually relatively easy to prove that the distribution of the potential outcome, which means, this basically means that if you can go have a population, if you can go to assign everyone hypothetically to the treatment, what the average outcome would be. This is a different quantity. This says that I just go to my population, grab the people who indeed take the treatment, what their outcome would be. So because remember, there's a selection in the treatment, who get which. These two things will not be exactly the same without any assumptions. But with assumption, with ignorability, these two things actually are the same. So this basically say that, well, this is my causal quantity, define my causal effect. This is what I can actually estimate from my real data. This is essentially association between y given z and x. These two things are equal. So that's why this assumption is so important. And because of that, what you can do is you just simply calculate. So what you can do is, once we call this outcome model, outcome surface. It's basically the outcome given the treatment and x. So in other words, so this is let's say this outcome, this is true outcome function. It's just mu. As mu is a function of x and z, the function of y as a function of x and z. So once you have this, and then you can, so this is all, identification. Again, another thing in causal inference is we separate identification and estimation. Identification basically say that, this estimand can be expressed by the true values of things, observed things. But estimation is you don't know this, right? So you still need to specify a model to estimate that. So it's a different concept, but it's closely connected. So here I can just, so what in practice we do is, given those results, I can just specify a model. Like very simple, go to the treatment group, do a regression. Go to the control group, do a regression. And then I can just use that to predict, for each person I can predict what is the outcome under the counterfactual, the alternative treatment based on those outcome, and then I can just I can just estimate any estimand you can think of, right? So if a Kate is just plugging the X, and if the ATE, I just average over everything. I use this mu hat. This is the outcome function that you predicted. You are using a model to fit to this data. Okay, so that is all very simple. This is called outcome modeling approach. That's turned out to be like the most relevant to the Bayesian analysis. So if you think of what is Bayesian is everything. You have a model, then model have some parameters, and then you have a prior for the parameter, and then you use the Bayesian crank, Bayesian theorem to get the posterior, right, of the parameters. So the key in Bayesian approach are two things. One is a model. Model on what? Model on the outcome model. In causal inference, model on the outcome model. And then you need priors. So those two things. So you can see that just fundamentally, Bayesian inference, if you want to do Bayesian causal inference, then a key is you need to have those outcome function models. We're building a model on that. And then, of course, if you're familiar with causal inference, you know that there are different approach of identification. Another approach is use the propensity score to inverse probability weighting. And another thing is called double robust or augmented IPW, combine the two. But I will, so for now, we will see that on surface, outcome model is a key identification framework to the Bayesian approach or model-based approach called inference. So, yeah, it's just it took me a bit quite some time to go through the background. Even though I know most of you know a bit about causal inference, I still think it's good to kind of give an overview of this and see where we are. So now let's say we want to do Bayesian inference of causal effect. So step back to think what's the problem we're really having is we have causal effect defined in counterfactuals. We're missing half of those potential outcomes or counterfactuals. So a very simple idea is if I can impute those missing potential outcomes, I'm good. Okay? So, or in other words, treating causal inference as a missing data problem, and then just impute those missing data, build a model, impute those missing data. And so let's think about this. So essentially, this is a problem like you are having, for each sample unit, I have 4 quantities. So 4 variables, y0, y1, z, and x. And 3 of them are observed. So of course, the treatment and x are observed. There's one here, particularly write as obs, is one of the 2 is observed, the other is missing, right? So then it's and I wrote this already before. So there's a given z, if you know who's treated, and which most of the time we do know, there's a one-to-one map between the observed data and missing data and the y1, y0. So what do we do is, so Bayesian inference would view all the quantities as random variables and then build a model for them. And of course with parameter, and then derive posterior inference of those, because those, so if anything, okay, so all the variables, the missing data, okay, the key thing is the missing data is viewed as also missing unobserved random variables. So we can also treat them the same way as parameters. I haven't get into the concept of parameters, but essentially we can impute, get the posterior predictive distribution of those missing y's. Okay, so from this perspective, missing potential outcomes are drawn from the posterior distribution of their posterior predictive distribution. So that's no different from them from unmeasured unknown parameters. Okay, what do I mean? So this is a key. This is a key slides. So this is where Sharon Lee's asked about the definity. It used to be like, it would be important to put here, but I simplify that. So the thing is, if you're Bayesian, you would need a joint distribution for all of these things. So this is where you'll start from, right? So this is a joint distribution of all the random variables, basically all the data I have for all units. So this one. And but I assume that this is governed. So the joint distribution, I basically assume that there's a joint distribution, and this joint is governed by a generic parameter. So I wrote this. So it consists of 3 parts, conditional on which this can be decomposed as the IID products of each unit. Unit version of that joint distribution. Again, this is just simplify things. So sometimes I evoke. I just make this. So this is just say the joint distribution can be, there's a parameter, exists a parameter so that they're IID. Okay. So there's some technicality there. I'm not getting into that. So the key thing is now I can just look at each of them. And then this is complicated. Even though there are 4 variables, it's still complicated. It's much easier if we can decompose this into something that is more doable. So if you look at this, so what does this mean so I decompose this into this 3 parts. The first part is z given, so it's a z distribution given everything else. Then is the outcome given x, and then is x itself. So why do I do this? So this part is, we call it assignment mechanism. This is how this describes the model for how the treatment is assigned. Okay, and this part is then once I condition on this, the z goes away, right? So this is say this model says what the outcome, we call it a potential outcome model or outcome model. So this says what the outcome model, what outcome is a function of the covariate. And then finally, it's just a covariate distribution, right? So this, now we are essentially decompose. We decompose the joint distribution, rather complete joint distribution, into product of 3 conditional distribution are arguably easier to deal with. So the key part is, remember we assume ignorability. If you still remember what is ignorability, just say that this distribution does not depend on y1 and y0, right? So this complicated part become just a propensity score model, the probability of z given x here, and this is, so this just become a propensity score, this is an outcome, this is covariate, okay? So then thus you can see that why, so it's also funny, people find ignorability assumption, why it's called ignorability, it's actually turned out to be it's a Bayesian concept. People know ignorability for the longest time, think, oh, it's equivalent to unconfoundedness, but it's really a Bayesian, initially, historically, it's a Bayesian concept, because why do we call it ignorable? It's because later, under some more assumptions, this part, this propensity score dropped out from the likelihood, okay? But this, keep in mind, this gives a path. This is a key contribution of the Rubin 78 paper. Give you a path to say that, well, this complicated joint likelihood can be defined. I haven't include the priors yet, right? But this says that, well, you can decompose into 3 models: propensity score, outcome, and the X itself. Okay? So I'm not sure whether I want to go. This has become too technical. So what I just want to say is then, well, oh my God. So okay. This is about the distribution. Remember, step back. What we want to do is we still want to do inference for all those causal estimands, right? For all those causal estimands, we still want to have those things. We want to do inference of those, and one is missing. So now we are looking at the likelihood, and then we can, based on the likelihood, we can possibly impute the missing potential outcome, and then we are probably good. So it turned out that technically there's some subtleties there, and I feel that it's probably, I'm not going into the details, but what I just want to say that it turned out the average treatment effect, there are actually different versions of that, and that will affect how you do the Bayesian inference. Very slightly, but in practice, the difference between all the 3 different versions are quite small. Just very quickly want to run through this, just say, well, it turned out that you can have a sample average treatment effect. That's essentially you are treating your sample as your target population. It's like that's all you need to know. So there's another one is the population. The common one we deal with is actually population average treatment effect. What I just want to say that if you really go into the technical part, you realize the population average treatment effect actually involves both the outcome. Like I use this theta y to denote the parameter for the outcome model. I use x to denote the parameter for the covariate. So it turned out that technically, the population version of average treatment effect actually involves both an outcome model and the covariate model. I mean that's just technicality, okay? And then the so what do I mean is that, if you are, people normally actually care about the population average because we don't want to just make an argument about our sample. We want to have argument about the whole population. But then in principle, you need to have a model also for X because that is just from theoretical perspective, that is there. But in reality, nobody really want to model X. Nobody want to, especially if you have a high dimensional X, like in epi study, in biostat, we have a lot of covariates, like the per characteristic of a person. Why do I care about Y? I care about outcome. Why do I bother to model this X, right? So what people actually do in practice, implicitly for a long time, is they condition on X. They're just a conditional x. So the sample I have, I just conditional on the x, and then I impute my potential outcomes, and then I'm done, right? So technically, that actually is a different estimand. That actually turned out to be a mix, a hybrid between this population version and sample version. So we give it a name. It's a mate, because originally I was thinking of a hybrid, then it become a hate. So that sounds really terrible. So it become mate. So what it really is just we actually don't model x. We just conditional on x, and then we are still have a parameter. And then this is usually, as far as I can see, in most of the Bayesian causal inference, this is actually estimand they are using. It's just they didn't even realize they were doing this conditioning. But again, that's all. Technicality is a very subtle difference, and in practice it doesn't matter too much. Conceptually, it's important to know what do we get at. So mate is just a convenient approximation of path, mostly done implicitly in Bayesian inference. So the concept of population sample mixed version of the same estimand applies to also non-additive estimands. So this is a general concept, not just for ATE. And then I have some example, but I feel that this is not too important. Have an example of, in a simple case, what are those different estimates would be. So I will skip that. So it's more important. So okay, now about how do we do inference? So now we get an idea of the estimand, different version of the estimand, and then it's really how do you do it? It turned out there are two different approaches. The first approach I already mentioned is you basically just impute the missing potential outcomes, right? Give for each unit. And I'm going to talk in a moment how to do that from the posterior predictive distribution. And then for each person, you just impute this host, and then you can just calculate whatever estimate you want. Well, the second one is, well, if we look at this guy, if we look at this, it's really, well, actually, let's look at this. It's really, if I know the outcome, the parameter of the outcome model, that's it. That's the only thing I need. So if I build a model, and then if my estimand can be written as a function of the parameter of y, then I don't even need to do this imputation. I can just directly, so what I can do is I specify outcome model, okay, and then express a causal estimand as a closed form functions solely of the parameters. So then I can just look at the parameters. I don't even need to impute those missing potential outcomes. So that's called the model parameter perspective. I will talk that more later. So this is all good. Because this bypass is pretty cumbersome. You impute the missing potential outcome. The downside of that is not always feasible. For ATE, this is easy because you can always write everything ATE in a closed form of the parameters. But you have some estimand like this, like the probability of y1 given larger than y0. There's no way you can express that as a function. Well, most of the time you cannot. Or something like principal straight causal effect. There's latent variables there, and so like ultimately we will still need to get to this part. So we still cannot avoid imputing. But philosophically or conceptually, there are at least these two things, a different type of approach. In practice, we probably need to use both. But the idea is that in this approach, you need to get the posterior distribution of causal estimand from that of a model parameters with or without imputing each missing potential outcome. So this all sounds pretty high level. I will give an example pretty quickly. Before that, then I talk. This is still about the model-based, right? I'm still talking about estimand. I still haven't introduced even prior. Okay, so now how do we do Bayesian? Do Bayesian, you have an outcome model. That's not enough. You have a parameter. Then you need a prior. You need a prior distribution for those parameters. So the question is, okay, what kind of priors we get, and on what parameters we should get those priors? We should impose these priors. So it turned out there's a third assumption. So this is something unique to Bayesian causal inference. In frequentist domain, you don't need this assumption, okay? And this turned out to be actually a pretty important assumption. The third one is called prior independence. So the parameter for the assignment mechanism, z, the theta z, and then for the outcome, And also for the covariates, well, if you are doing the conditional do the mate, you don't need to worry about that. But the key thing is the parameters for these two different models, they are a priori distinct and independent. So this is actually turned out to be a very important assumption, and in high dimensional cases, it turned out that it's basically act as informative prior. I will get that in a moment, but this is assumption also for the longest time. People do Bayesian causal inference, take it for granted. And as later I mentioned that actually Francesca did some nice work on not relying on this, but that's for later. So anyway, so once I have this assumption, what we can do is we can just impose separate priors for each of those parameters. And then, remember, I have my likelihood. I earlier had my likelihood. And I impose this prior independence because of priors. This become, so now I will use the Bayesian crank. I have my posterior distribution of all these parameters. So what are those? This is just proportional to the likelihood and times all the priors, right? So this all looks like this. So this is about the outcome model. This is about the treatment assignment. This is about the outcome model, okay? And so we know that the posterior of the so we know that for the for the population version of ATE, it doesn't really depend on Z, right? Doesn't depend on Z. So this part, the propensity score. So this one has nothing. So if you assume ignorability, the treatment assignment has nothing to do with Y. So this section doesn't factor anything into the ATE. Okay, so this part goes away. So that's why this is where the name ignorable come from. So it's very interesting that you can see that ignorability, this concept actually was a Bayesian concept. But people take it for granted. It's like, it's funny that we will talk about ignorability and then didn't realize, well, this is actually originally was a Bayesian concept. So why is it ignorable? Just say that, well, the propensity score or the treatment assignment can drop out from the likelihood if you are assuming the prior independence. So then in the end, we just come up with, we just need to worry about this part and this part. As I said, in practice, we usually don't want to model this. We just condition on this. This part also goes away. So everything important is just become an outcome model and the parameters for that outcome model. Yes?
And I'm wondering if at some point you will be talking about the challenge of Bayesian inference in this context, because if you want to be, I know you're going to, I'm wondering whether you want to go there, and I think it's important to for the discussion, is the fact that if you want to be fully Bayesian, right?
Absolutely.
To estimate theta z,
Yes.
you need, from a Bayesian viewpoint, you're going to get the posterior distribution of theta z.
Absolutely.
All of the data.
Absolutely.
Which means, and I mentioned this because I remember presenting some of the initial idea of Bayesian causal inference to Don Rubin, and he got really mad at me because when I presented this initial idea, I said, well, I'm Bayesian, so when I'm going to estimate the posterior distribution of theta z, conditional to all of the data, which means I'm going to use the outcome data to inform the estimation of the propensity score, which would be a huge violation.
Absolutely.
Right? So I think it would be interesting for you to elaborate on that, because that's different.
There was a discussion about that in one of the
that's precisely, so I want to get to the point. Yeah, that's a feedback issue, right? You actually, Corey, wrote several very important papers. And also, in some sense, it's also this, originally I got confused. The biggest question bothered me when I read this review is, what's the role of propensity score or assignment mechanism in all of this, right? So yes, that's actually the core, I feel, that's the most important part.
Yeah, and it's exactly where Bayesian inference and
precisely.
Propensity score gets
precisely. That's kind of the main thing of the
war.
Yeah. It's actually not a war. There seems to be there's actually a reconciliation later.
Exactly.
Yeah. So
now is.
yeah. No, well, the thing is, Don will get mad no matter what. So I'm not surprised, right?
Well, the discussion was written by Wasserman and Jamie Robbins.
And then later, well, that doesn't help, right? And then another guy, well, not guy, is a Nobel laureate, Chris Sims. Actually, they wrote. Larry Wasserman and Robbins wrote this. This is a very classic, epic back and forth debate of this, and I will talk about that. Actually, that's the central problem to me that in this case. But I'm spending a lot of time to talk about the basics because I assume that most of the people probably are not aware of like those subtleties, right? So this is something I can quickly skip because those are more technical. Basically, say the 4 different versions of paid and mate, they don't depend on the correlation between y1, y0, and the sample version does, so it's slightly more complicated. So those are not too. The key idea is this part. It's like most of the time if you do Bayesian causal, okay, so the thing is, really, once you have this prior independence, which is actually a very strong assumption, these 2 things, you can throw away this thing. But life is not that easy, actually. This actually turned out to be an important one, so I'm going to talk about that later. But if you assume this, then you can just focus on this outcome model, okay? But that becomes this paradox. So all of this technicality stuff, I'm not going to, so you can do standard data augmentation, impute the missing outcome and stuff. So I don't think that's too important. So I always spend, so what, in reality, what do we do? How do we impute the missing potential outcome? We build an outcome model, and then we are essentially using we are like for the treated units, we impute the missing missing y0s from the y1s, and for control, we're doing the opposite, right? So imputation critically depend on this outcome model. Okay, so this in high dimensional is also critically depend on the priors. Those are pretty standard. So I also have some example. You can look at the slides and like to the simple bivariate normal distribution, and then you can actually derive this. You can use Gibbs sampler. You can use the standard Bayesian technique algorithm to impute how do you impute. Those are all standard, so I don't think that it takes it worth going there. But one thing I found when I was writing a review, I realized is important is also what does identification mean? Identifiability mean? This is also an important issue come up again and again. So if you are frequentist, we talk about something identifiable. What we meant is, well, the parameters can be expressed as a function of the observed data. So it's a clean cut. Parameter is either identified or not. If you're Bayesian, things actually become a bit fuzzy. They turn out to be a different version, different view of what does identifiability mean in Bayesian, of Bayesian framework. So original Lindley say that in 72 say that, well, as long as you have proper prior, your posterior is also proper. So then all parameters are identifiable. That is not particularly helpful because we know that in causal inference, we know some parameters, you don't have data at all. So for example, I have y1, y0. For the same person, you never observe both. So if you care about the, say, correlation between y1 and y0, you never have data about that. So from frequentist, you would say clean cut is not identifiable. But the Lindley would say, no. If you can have a row, you can have an association. If I have a proper prior for this parameter, this is identifiable. And Lindley would say that's identifiable, but that's not very helpful because your prior will be exactly the posterior. So then I think that Gustafsson has a much more useful concept. He said that, okay, so he said that the identifiability in Bayesian paradigm is really a continuum. It's between 0 and 1, from weak identifiability to strong identifiability. So it's not like a 0, 1. So he's saying that identifiability depends on how diffuse the posterior distribution is. So if you don't have enough data, your posterior might be very diffuse. Then that is kind of weak identifiability. So again, this is all high-level discussion, but this turned out to be very useful in causal inference. Like so So why it's important in causal inference to differentiate that is because weakly identified parameters actually are common, because anything about the correlation involve two potential outcomes. It is because you don't have data for that. You would have this weakly identified parameters. And also another example is if you are doing principal stratification, some estimand is defined on some latent structure. Then that's just by default, it's weakly identifiable. But then it's not that you cannot do anything about it. It's still, they're weakly identified, but you can use data assumptions to make it more strongly identifiable. So it's kind of important to get this point is that, you want to get this point out. It's like when we talk about identifiability, particularly when we talk about Bayesian, it's a continuum. It's no longer 0, 1. That's another difference between the frequentist and the Bayesian. So then, importantly, I prepared more slides than I think that I thought I could cover, but that's good. You can skip. So anyway, with all of this discussion, the key, what I want to say is the key task in Bayesian causal inference is, particularly in complex estimand, is to model the outcome model, right? At least for now, it looks like that. At least for now, the propensity score doesn't seem to play a role. Well, other than it's not that simple. So there are two general categories. One is called S-learner, the single learner. Basically, you build a single model of these two things, this outcome model. Or it's like the simplest case is a linear model with an interaction term between the X and Z. Or the so-called two learners, two separate models for each group. So for each group, then you can do this. So for linear models, these two approaches the same. But in practice, so now more and more in high-dimensional, people use like the machine learning methods, like the trees, the forests, neural networks, and then in Bayesian become very popular. You can use BART, GP, and DP mixture. So there are many of this kind of models. But you can see that really this whole approach, why I spend all this time talking is, well, after all of this, the important, at least for now, is to build a model just for the outcome, and then you kind of don't need to worry about anything except that you cannot. But for now, so then in Bayesian, we use a different, just the priors to do that, or model. So the most famous one, most widely used is called BART, or it's BART. I assume you know something, but if you don't know, to me, it's essentially a Bayesian version of random forest. So you have ensemble of trees. Then random forest will use the ensemble of the trees to come with one summary prediction. And BART essentially use prior to regulate how deep the tree you want to go, and how do you split. So that is just think of BART as a Bayesian version of random forest. Okay, so this is a landmark paper in the Jennifer Hill in 2011, saying, well, why don't you just use the BART model for this outcome model, and then just an outcome model, and then you can just get the posterior distribution for the parameters and things like that. But this idea will later actually much advanced by those folks, Hang et al. So they're saying that, well, no, it's better to reparameterize this guy, reparameterize the outcome model into two parts. The first part is the baseline distribution of the outcome, and the second part is capture the treatment effect. So this is like a Z. So the key thing they say that, well, to make the key thing they realize is, well, we care about treatment effect, but the baseline distribution of when there's no treatment might be much more complex, and we don't want to be the complexity of the two to be the same. So the idea is that if I reparameterize that, if I give a separate prior, they say, well, particularly they give separate BART prior for this baseline distribution and for this kind of capture the heterogeneous treatment effect, give separate BART prior to this. This will work well. So they empirically also showed well. So this is essentially a reparameterization of things of the outcome model into two separate BART priors, and that's supposed to, they call it Bayesian forest because there are two two BART, and then it's already, each BART is already a forest, and then two, of course, is a forest. So that's called Bayesian forest. But the idea is also on the Bayesian. It's really on the reparameterization. So there are many, it turned out this become really popular, and people start to extend this whole idea also to survival outcome, and then it also won a lot of like data competition. In some causal conferences, they have data, and then people use BART, particularly for use the Bayesian random forest. Those ideas very often beat like random forest, this type of approach. So that's all good. But you can see that so far I still haven't talked anything about the propensity score, which is like ignorable. But obviously there's no free lunch, right? So it's really, so this is the key part. I think I probably will I'll give the paradox before we take a break, and then the second half we'll talk mostly on this. So this is really a paradox like of the role of propensity in causal inference. Right, so first, so far we talk on the ignorability and the prior independence. The propensity score is ignorable, right? So that's ignorability. But we know propensity score plays a central role in causal inference. So it's very funny, right? In the propensity score paper was the Rosenbaum-Rubin 83 paper. The title of that paper is the central role of propensity score in causal inference. And so this paper also was originally, the ignorability concept was first proposed in the Rubin 78 paper, say, oh, it's ignorable. This paper says it's ignorable, this says it's central role. Like, so obviously on the frequentist domain, it's central. And with a vast, also empirical evidence, this is important, right? So then this seems to be a paradox. And also I like, okay, so I should have go back to very later, talk about, I like this quote from Don Rubin, even though I don't always agree with him. I like some of I like his quote. He said that any complication that creates problems for one form of inference creates problems for all forms of inference, just in different ways. So if propensity score is so important in frequentist domain, there's no way Bayesian can just magically does not depend on propensity score. But where does it come from? Where does it, where the role actually, where does that come from? So that was actually important. And so then if you think, just step back. When we do causal studies, causal people always say that, well, there are two different stages. One is called design stage, the other called is analysis stage. So design stage, in causalism in particular, means that anything, in collect data, anything that has nothing to do with Y. And design stage means anything has anything to do, so that has something to do with Y. So Bayesian modeling, outcome modeling, if you assume those assumptions, prior independence, ignorability, then it seems that only involves the analysis stage. Where does the design stage factor in? Okay, so then that will become a problem. Then I realized this a very important observation is, if you do causal inference, if you do the propensity score stuff, you know that this concept of overlap and the covariate balance between the two groups plays a central prominent role in the design stage. Like people do matching and weighting so that the two groups look very similar. How about Bayesian? Bayesian, if you just do a model, it seems that you don't get anything. Like in the model itself, so one thing I realized is when you build a model a function of y given x and z. But the model itself doesn't tell you anything about the data structure, how similar these two groups look like. So remember, causal inference is about comparing two groups. Well, actually, two hypothetical groups. So but it's a counterfactual comparison. It's not just a prediction, right? So then this is important. So this is where actually things become tricky. That how do we, obviously this should play an important role in Bayesian, but if we assume prior independence, we kind of throw that away. And so then it's become a push. Well, later the feedback issue actually Francesca mentioned is also another, I would say, another motivation here. So well, then why does overlap or propensity score or balance matter? So this is the key. So if the outcome model is correctly specified, again, quoting Don Rubin, is if God comes down, tells you the true model, then that's all you need. You don't need anything extra, right? The posterior distribution of theta y is correct, and that's all we need. However, outcome model are rarely correctly specified. So whenever that model is not correctly specified, especially in the region, in the area that there's not enough, either all treatment group or a control group, or in other words, there's very little overlap, then everything you have essentially is a model. So it's purely based, everything model-based causal estimate, whether it's Bayesian or just a frequentist model-based. What you do is it relies solely on extrapolation. So what's the problem of extrapolation? It's again, if your model is correctly specified, great. If it's wrongly specified, it can be very far away from truth. So in other words, it can be very sensitive to all the outcome specification, right? And also we want to correctly quantify the uncertainty accordingly. Okay, so this is a key. So the one key thing is outcome model itself does not take into account of the overlap take into account of that. So then it's really important to put the propensity score into this outcome model framework. And so I have a toy example basically to create a case that you have a complete separation of treatment group and control group, and then things are really complicated. I don't have time to talk about that, but I give you 5 minutes. But then I would say that then people realize, well, even in the Bayesian approach, the outcome model is just a part of the game. So you really, even in the Bayesian approach, maybe in the Bayesian approach, you can do something. At least you can do two things. First is that, well, Bayesian model, if you just look at the model itself, it's purely about the analysis stage. So then in order for you to do Bayesian, you need to first have a good data, Good data, what means that I first ensure good covariate balance initially, and then on top of that, I do a Bayesian model. So of course, the most extreme case is if you can have the luxury to randomized experiment, you can have a randomized experiment, and then you can do Bayesian model on that randomized experiment. So there's a very famous result from Fisher and then later to Winston Ling is really say that if you have a randomized data, that in principle will be well balanced, the treatment group and control group are very similar, then even if your outcome model is misspecified, doesn't matter. You still have consistent results. So that's a very well-known theoretical result. Why is that? It's because if you are having a very well-balanced or randomized study, so in any part of the data, you can just non-parametrically go to calculate y1 bar and y0 bar. You do a model, it gives you a little bit more efficiency, but in principle, you don't need it. So that, of course, the most extreme case. That's when you have the treatment group and control group are perfectly balanced. And then observational study, we don't have that luxury. So what we should do is we should first actually make the data, so use a propensity score to matching or weighting, whatever, to make the study very close to a randomized experiment, as close as possible. And then on top of that, with that data, it's like we do a model-based approach on a matched data set or on a weighted sample set. So the second, so this is the first way you can do. And another approach is, of course, if your model is sensitive, at least try to make it as flexible as possible make it flexible so that it's less prone to model misspecification. So that's why the idea like use Bayesian non-parametric models, those are very useful. But again, I would argue that if you do well here, this approach is more secondary. So then this turned out this idea of why don't we just directly incorporate propensity score into outcome model? But then that also it's an open all the can of worms that as Francesca mentioned. So that's after 5 minutes break, we'll come back and then revisit this issue. The second half is a bit more interesting, like more core to the issue to Bayesian. So I want to go a bit slowly here. Talk about this. So remember last time, just a very quick recap, we realized even on the contrary to so there's almost a paradox to say, oh, on one hand, you don't need a propensity score or assignment mechanism. On the other hand, you definitely need. So where does the reconciliation come from? Well, then for a long time, people realized, well, after many years exploration, all the authors come into the same conclusion, that is, even as a Bayesian, propensity score still play a central role. So, but if you're Bayesian, you do a model, then where does that come? Where does that propensity score get into the outcome model? Well, you can directly incorporate propensity score into the outcome model. Okay, so there actually turned out to be multiple approaches. There's no consensus of how to achieve that, but there are some approaches here. There are at least 4 different approaches. So this was originally so the first approach is just purely use propensity score as a covariate. So remember, propensity score is a function of x. So just to use that as a covariate. So this was originally come from the earliest one from the Rubin 85. So he said, well, why don't you just use the propensity score as the only covariate in the outcome model? Because if you know anything about propensity score, you know that propensity score is supposed to be a one-dimensional summary of all the covariates. So turned out that that's actually not a good idea. Because plenty of studies show that this is turned out to be that the propensity score as a dimension reduction tool is too drastic shrinking. So with this, you are actually turned out to be sensitive if you just use this as only covariate. So then this is get to Corey Ziegler and also Francesca. They did a series, very important paper, is they realized, well, instead use the propensity score as additional covariate. Okay, so that is actually a very interesting idea. So instead, they say that, well, you use a propensity score here as additional covariate. So you have this outcome model, but you use propensity additional covariate. I will talk about that in a moment. So why do you do that? So if this actually later turned out that this is almost like a Bayesian analog to double robustness. So let me explain that in a moment. So when you put the propensity score, again, this is quote unquote true propensity score. You can put the true propensity score there. So this is the thing, if the outcome model is indeed correctly specified, you're adding the true propensity score. I mean, in the end, we don't have the true one, but if you put propensity, because the propensity score is a function of x, it's like this is auxiliary. So if the outcome model is correctly specified, adding this, it's redundant. You don't gain anything, but you don't lose anything. You lose 1 degree of freedom, but that's all the price you pay. But the key point is really this. If the outcome model is misspecified, which most of the time is the case, then adding the propensity score here as additional covariate, you are actually almost like, you are actually doing something like this. I always say this is, so what do you actually do? Just think of a linear model. Think of a linear model. You have x, z, and then propensity score as additional covariate. What you're really doing is almost like, you're like given each particular propensity score value, you're doing a regression of x and z. So in a sense, it's like a continuous version of stratification. You first, almost like you are stratifying the data first by the propensity score, and then within each that small stratum, you do a regression, right? So of course, this is a continuous version of that. It's slightly more complicated. But so in other words, that when the outcome model is misspecified, because you are first, this propensity score, adding this is almost like an anchor. The anchor is so that it's doing this stratification type of thing to make sure that the treatment group and control group are similar in covariates. So it will be less sensitive. So that was the idea. So then I realized this is basically a Bayesian analog of double robustness. And then some people actually indeed mentioned that. So that is, in other words, funny enough, to put the propensity score as additional covariate, you are actually doing a continuous version of mixing the propensity stratification and outcome modeling, and you are actually achieving double robustness. So that's actually very cool. And then there are actually different approach of doing that, right? Different approach of doing that. So this is, I think, Corey's paper and Francesca's paper. They were talking about, and later I will talk about this. In practice, we don't have this. We have E hat. Then, but they show that for the first time, as well, I know that adding the propensity score is ultra important, because that stabilizes a lot of that make the inference much better. So then, actually, this idea was kind of independent, discovered by multiple groups of researchers. So you still, the key thing is you still want this model to be flexible. So Raw-Little and colleagues have several similar ideas, but they're not Bayesian. They're just purely, say, the model-based. And then this paper, they're the first Bayesian version of that. So those they also similar idea. The similar idea is, okay, I'm going to reparameterize this, still use the propensity score as an additional covariate. But what you do is you're having a parametric model here of the treatment effect, like the X and Z. But then everything else, everything else is you use a propensity score, use a non-parametric like penalized splines, so you can achieve this double robustness. It's a similar idea, but it's just different parameterization. And as I already mentioned, the Han et al. Paper have this Bayesian causal forest. Remember, they were saying that a few pages before, I said that their idea actually was to separate the outcome model into the baseline model and the heterogeneous treatment effect model. But then they say that after did many numerical examples, they realized, well, if you want to do this really well, you have to put the propensity score, like it's a good idea to put the propensity score in the baseline model. They find that adding this make this similar as Ziegler's discovery that putting the propensity score in one part of this model, in this particular case, the complicated baseline model, that improves the estimation much, much better. Okay, so then it's crucial to include this propensity score into this basic part of the model. And then there are other researchers, Roy et al., like Michael Daniels, they like to use Gaussian process priors into those, but the parameterization is still the same. But whether this is a frequentist, this is Bayesian, but no matter what, the key idea is you need to put the propensity score into this outcome model somewhere. You cannot do it. If you don't do that, you will, practically, you will run into very poor performance. Okay, so now this is a feedback. This is the issue that Francesca mentioned earlier. So think about this, adding the propensity score into as an additional auxiliary, but important auxiliary covariate into outcome model is not a new idea. It's originally also causal inference is also very related to survey. Okay, so in the survey literature, for the longest time, people use the sampling weights to augment the design, the so-called design-based estimate. Essentially, they use the sampling weights as a predictor. And sampling weights it's basically propensity score. It's a functional, it's an inverse of propensity score. So this has a tradition, okay? But in practice, there's some practical issue there is, well, we don't know the propensity score in observational study, right? We need to estimate it. So we need to have an E hat. We estimate this and then plug in the E hat into the model we specified. Okay, so this is what we will do. But they start to have controversies. Causal people tend to argue. And they are some for philosophical reasons, some purely for personality. So for controversies, and also Bayesians are very philosophically, they're also a different type of people. So you can imagine there's two groups of people getting together, right? So some Bayesian people, well, I think Francesca firsthand had experience, right? Like this is really not dogmatically Bayesian. Because your first estimate of probability, you do this two-stage thing. So I will talk about this point in the next slides. But this is really not the first thing Bayesian would do. But okay, so let's first talk about the causal people, what they are arguing. They're saying that this, no. Why does the true outcome generating process, basically the outcome model, depends on the assignment? Just like the truth, how the underlying truth is, that should have nothing to do with how I design, how I instruct the study. I don't personally, particularly Jamie Robbins, they are really against it. They wrote a series of papers against that. For me, it's not a big problem because I use it as auxiliary kind of tool to deal with. I don't really think the outcome model depends on the propensity score. This is just purely auxiliary. So I don't think philosophically this even is an issue, but this was original the issue. But I think a bigger issue is probably this feedback. Okay, so let's step back here. So in a full Bayesian world, So if you're really Bayesian, what you do is you model everything, right? So a natural way will be simultaneously infer the outcome model and propensity score model, not do this two-stage thing. So instead, so you will have this, you model this, and you will do it together jointly. And then, so the key, also Bayesian would say that, well, if you are just the first estimate the propensity score, and then plug in, you basically ignore the uncertainty in estimating the propensity. Okay, so those are all issues. Why don't you just do simultaneously, and then you don't have that problem? Well, so the idea is doing so will allow the propensity score estimate, the propensity uncertainty propagation in the final estimate. So again, life is easy when the outcome model is correct. When the outcome model is correct, you don't need to do any of this. The problem is when the outcome is misspecified, this creates a huge issue. Because then the propensity score, so if this is misspecified, remember, if this is correctly specified, this is auxiliary, it doesn't provide any additional information. But if it's misspecified, then the propensity score will actually affect the outcome model. So then that is strange, because then the propensity score model would be informed, so because you're also doing these two things simultaneously. So it's kind of one would affect the other they will affect each other. So then the propensity score estimate would actually go back to be informed by the outcome model. So it goes both ways, because if you model both things in the same simultaneously, so whatever in one model will feed back to the other model. So that's called a feedback issue. Because why? Because remember what unconfoundedness assumption said. Unconfounded assumption says that the assignment mechanism have nothing to do with the potential outcomes. But here, if your model is misspecified, the outcome model actually will inform your propensity score. So that is just violation. Like when you have a misspecified, it violates the unconfoundedness assumption. And theoretically, this is conceptually, but practically it will just completely distort your study, right? So this is called the feedback. So empirically, when the outcome model is misspecified, the joint model lead to very severely biased causal estimate. And I remember Corey probably first run into many of that problems and then realized, well, we have to cut this feedback. So that's from a traditional Bayesian perspective, what are the issues, what are the strange problems there. So again, I talk about this. So then Corey actually from that, or Francesca, from that perspective, they realized, this feedback is really a problem. So in order to cut the feedback, then they realize, go back to the original, we have to do this two-stage thing. Is we first build a Bayesian model for the propensity score, and then we plug in the posterior jaws of this propensity score so that we take into account of the uncertainty in the first stage into the Bayesian outcome model. So then, this is actually mercantilist approach. Or then this is actually still a bit cumbersome approach, but then Corey realized from this perspective of cutting feedback, realized it's essential to actually, you have kind of no choice but to add the estimated propensity score as an additional covariate into the outcome. I'll have to do this two-stage thing. So this is another, like only yesterday I realized this is actually, in retrospect, I would say this is another motivational of the one we deal with is the paradox between reconciliate the role of the propensity score in a model-based approach is cutback is actually another angle to say that why cutback is another angle why we have to get propensity score into the analysis. But again, really, if you are full Bayesian, this is if you're full Bayesian, like some people in my department, this is really very uneasy because this is not full Bayesian. They will yell at you, right? So then I feel this is a self-inflicted problem unique to Bayesian inference. Why do you even do this? So like you want to do Bayesian, but then because of Bayesian, you have to do this two-stage. You first estimate propensity score and then plug in the propensity score, and that becomes not Bayesian. So then what, right? So again, if you're a causal person, or you're a practical person, well, I'm not saying full Bayesian or practical. I'm just saying that if you do a real analysis or real applications, realize that the debate of those are not very important. It is really about how do I get have a model, a complex model enough to deal with the problem in hand, and how can I get a less biased, like a good result? And then, so again and again, from all different concepts, different angles, we realize adding the additional covariate, the propensity additional covariate is a good way. So another approach, actually, I love this approach from academic perspective, but practically it is a different matter. So another group of researchers say that, well, a lot of those trouble actually arise because we assume this seemingly innocent assumption, say independent priors for, we assume that this prior independence say that the treatment assignment and the outcome model, they are a priori, the priors, the parameters are a priori distinct and independent. So we made that assumption just by, just few convenience. And it turned out that this is actually a very strong assumption. I will tell in a moment. This assumption is not as it actually has strong consequence. So then the idea is that why don't we actually specify priors? We don't need this because this might not be the case. So we can specify priors for outcome that is dependent on propensity score. So we actually say these two mechanisms, assignment mechanism, outcome mechanism, they are related to each other. So we can use, again, the strength of Bayesian is you can have you can specify priors to reflect that. So this is one point paper is by Wang et al. Again, this is both Francesca and Giovanni on that paper. So this paper is a very good example of that. So what they do is they specify dependent prior for variable selection in both the propensity score and the outcome model, and then make them dependent. And then there's some other attempt in the literature also about this idea is to design some Gaussian process prior stuff. But so then, yeah, as I mentioned, that there's actually epic. There's Ritov and Sims also give similar attempts of this. So I give some example. This is, I don't know, I mean, how many of you know the spike and slap prior? Maybe not. Okay, so I'm gonna skip this part. So the idea is this paper basically say that, well, if you have a propensity score model, you need a propensity score model, you need an outcome model. And in both cases, you have a lot of covariates. So you want to do some selection, right? You want to select your propensity score model, you select your outcome model. So this paper essentially designed the prior so that allow let's say, basically allow how likely this covariate is included in the propensity score model is correlated with how likely this is included in the outcome model. Because often in practice, they are correlated. So that you can actually devise a very clever way to design that. And so in that case, you're basically allowing the propensity score model and the outcome model are a priori related. Okay, so this is all very nice, except that nobody uses this because it's complicated. It's like you have to tailor-made almost for any problem you have. And people like simple. So this prior essentially forces the propensity score to enter the posterior inference for the average treatment effect. So this is a nice idea. And then there's another idea. It's also by Little 2004. This is actually a very clever mathematical construction, but sounds weird when I look at it. So this is, people remember so far everyone was talking about put the propensity score in the outcome model directly, like that's the mean of the outcome model. So this paper, they find a clever way. They say, well, if I build an outcome model for the treatment group and for a control group, the difference is they put the propensity score they use the propensity score to kind of characterize the variance. So it's really a very strange, I'll say a very strange construction. But what they proved is that if the propensity score are known, then the posterior mean of the average treatment effect coming from this construction will just look like it's essentially the hierarchy estimated. So it's a hierarchy estimator is just it's a fancy version of it's a normalized version of IPW, right? So then they are so if the propensity score unknown, the posterior mean of this is closely related to. So the point is that you can do this construction so that the outcome, so the propensity score directly enter the outcome model, and the strategy into the PS additional variance. Into the conditional variance rather than conditional mean of the potential outcome. So they're also, very cool idea, but not very useful. Because not very useful in the sense that it's just you have to design this thing for almost every case. Like it's very case by case. Nobody has the time to develop those things. Okay. So then for the longest time, people still assume this just use the approach one. But this is a very cool method. So the third approach is also this. It's also a paper Francesca is on. Francesca is on all of it. So this is actually there are several authors. So this Julia Antonelli and Georgia are both a student or postdoc of Francesca. So they have this idea. They say that, I didn't talk about double robust estimation here, but double robust estimation is basically IPW estimate. So it's combine IPW and the outcome model, right? So you have this double robust estimator. So their idea is, why don't I just specify a separate model for the propensity score, a separate Bayesian model for the outcome model, and then I just have the posterior predictive distribution from both models, and then I use the double robust formula, just combine them. I remember the paper's name is a marriage between, it's a marriage between double robust or a perfect marriage or something. Anyway, so it's basically
it has been written by two married couple, me and Giovanni and Joy and Georgia.
That's two, So there are four authors and the two couples. Then the paper's title is some marriage.
So fragmentist and Bayesian.
I see. Yeah, anyway, so the idea is actually to combine really use the double robust estimator as a form to combine these two different posterior distributions. So the advantage, and then they prove the asymptotically the consistency. Actually, you can prove the frequentist properties of this kind of pseudo or half Bayesian approach. So it's easy to implement. Flexible choice of the models and the proper uncertainty quantification. This is all proved. This is a very nice paper in biometrics. Again, some people don't like it, especially for Bayesian. This is for pure Bayesian. Again, in my department, this is hard to stomach because this is not dogmatic Bayesian. Because how can you do this two things separately, right? But then by this point, by now you probably see like why is people so insist on being dogmatic Bayesian? Some people are. So the last one is also a strange approach. It's not strange. It's almost like why? So Bayesian bootstrap. How many of you know Bayesian bootstrap? So Bayesian bootstrap, you all know bootstrap. And then once Bayesian bootstrap, okay, so Bayesian bootstrap, it's a paper by Rubin in 81. The paper, if you go look at it, is 5 pages in annals. Nowadays, you never see 5 pages annals paper. Everyone writes papers too long, like 30 pages stuff. But it's a great idea. So it's technicality I'm not going to say. It's basically a general strategy. It's a non-parametric strategy to simulate posterior distribution of any parameters from a non-parametric model. So basically, if you have a non-parametric procedure, you can use it. This is just a procedure of it's essentially a reweighting. You're doing bootstrap, but you're reweighting. You don't need to know the details if you just know that this is general strategy because you can prove that it's turned out to be the limit of the inference of a derivative process prior. So remember when we talk about, I didn't talk about IPW or double robustness, but these two type of approaches, they are Bayesian. They're not Bayesian. They're model free. They're non-parametric. So essentially, you use this procedure just can crank you can turn any non-parametric estimator into a Bayesian, basically a Bayesian approach. So it's just a general recipe to converting any frequentist non-parametric methods into a Bayesian approach. So there are several attempts in the literature about that. This one, I actually do have, as a half-hearted Bayesian, or Bayesian wannabe, I actually have problem with this one. Because I was asking myself, what's the advantage if you what's the advantage? Is this just purely being Bayesian for the sake of being Bayesian? Because you are essentially converting any frequentist approach and use this Bayesian bootstrap to make it Bayesian. But then what's the point? Really, like there are other ways. But there are people who does this. So that's another approach. But you can see in all of this, it's because this involves a propensity score. This also involves a propensity score. So you can see that this way, propensity score was also included in the Bayesian inference. So there are just 4 different approaches. I would say that the first one is still the most widely used, and also, to me, I think is the most elegant and useful way, also practical way, just to use the propensity score as an additional covariate, do this 2-stage approach. Okay, so then that is the about how do you involve propensity score into the Bayesian analysis. So first, we already said that it turned out from any aspect, propensity score, it become clear, propensity score play a central role also in the Bayesian analysis of causal inference. It's just how do you incorporate that? There are different approaches, and then we showed that. So now we jump into another section. Another important, it's just like we know that high dimensions always change the game. So high dimensional data bring additional challenges. When we talk about high dimensional, actually we usually there are 2 different regimes. So there are two different things we're talking about. The first is that, well, if you have, most people probably think about high dimensional as high dimensional covariates. It's like I have a lot of covariates. I have high dimensional. I need to control that. I need to do model selection, things like that. But if you're Bayesian, you know that high dimensional, we also mean something like this. Model itself has a large number of parameters. For example, non-parametric models. They have a lot of parameters. So like Bayesian non-parametric models, they are high dimensional. So in reality, the model applications usually involve both problems but encountered. So then let's step back to think about what Bayesians do in high dimensional. There's a huge improvement in Bayesian approach to high dimensional study outside causal inference. So what people usually do in Bayesian is like first called, so infrequent is a high dimensional, of course, is regularization. Statistician usually is we're pretty bad in giving names. We call penalty. You know, the penalty sounds so terrible, but in machine learning, people will say regularization or sounds much nicer. So Bayesian is, so we use prior to informative prior on the parameters to achieve regularization. For example, Bayesian lasso, Bayes lasso, or many different type of things like the Bayesian non-parametric priors, similar as sparsity priors, spike and style priors. But again, the key feature of Bayesian high-dimensional methods is to use informative prior on the parameters so that you can do prior selection. You can force sparsity into the parameter space. So then that becomes very important. So for Bayesian, it's very important what kind of priors you choose. Okay, so the choice of, remember, we are talking about outcome model. We were earlier say, well, you can do an outcome model, but if you have low dimensional, you can just have your linear model, and then, does it have a non-informative prior, everything's fine. But if you are in high dimensional, you almost always forced into some more advanced models here. Like we often say barred prior or GP prior. Those are essentially themselves are models. Okay, so then the question is, you can choose barred prior. You can choose Gaussian process or DP derivative process or Polier tree. There's so many priors you can choose in high dimension. I mean, in low dimension, there's no point of doing all of this. High dimension, you have all the things to do, all of this priors you choose, but which one to choose? This is another thing, like the frequentists say, well, I don't want to do Bayesian because if I'm a frequentist, I just use my lasso, use my regularization regression. I don't have the trouble of choose the priors. Okay, so then then in Bayesian you have this additional tool of incorporating information from the data information from the priors to help you. You have this is a double-edged sword. On one hand, you have a prior, informative prior can give you a lot of extra power that the frequentist approach cannot achieve. On the other hand, you have this additional task. You need to choose, make a good priors. So which one to choose? So a lot of people say BART, because BART indeed is very successful in many cases. But back to my original point of doing any model, I mean, even prior is a model, right? Prior essentially in the high dimension is a model. Doing any model, if you don't look at the data, the model itself won't tell you anything about the data. You need to incorporate, or let's say this way. So ideally, so in causal inference, a key thing, so what is special about causal and Bayesian? So the key challenging case in causal inference is the region when there's no lack of overlap. So remember, as I mentioned, that if you have randomized trial, life is easy. You can just go to calculate the y1 bar minus y0 bar. But once you have, what is really complicated in practice is when you have a data that the treatment group and control group look different. So then how does a Bayesian approach, like outcome approach, take into account of that? That's important. So I would argue that a desirable prior should accurately reflect the uncertainty for various degree of overlap. So my point is that if I look at the data and find that the treatment group and control group are very different, so in other words, they have lack of overlap or they are not very balanced, then a good prior should adaptively let me know that in this region I have less information, then should give more uncertainty. Okay, so that was the idea. So that, I mean, again, the Bayesian, why do people do Bayesian? One key reason is Bayesian can give good uncertainty quantification. But in causal inference, a big source of uncertainty comes from the degree of overlap between two groups. That's very special about causal inference. So then if you're doing Bayesian, of course, you want your prior to accurately reflect that. So then this becomes, yes?
Can I ask you how you evaluate that aspect?
Oh, wait, I'm going to give an example. Yeah, I don't evaluate, I'm just like, okay, so this is a fun example. So I did a simple example to kind of showcase. It's very hard to evaluate, but you kind of know, depends on how you see the prior is constructed, you will have idea. Some are good, some are not that good. So I construct a simple example. So this example is, I have only one covariate to make life easy. So I have a treatment group, I have a control group. So you can see that, and that this is, let's say this is H. So that's so you can see that these two groups, it's only in this middle part there's some overlap, and then in these two parts, the covariates, like the two groups look very different. Okay, I mean I'm saying the covariates, it's just the covariates, and so I fit. This is a constant treatment effect case, a toy example. So what I did is I showed what I did was, oopsie. So, yeah. So what I did is I simulate this data. It's a constant treatment effect. It's around it's around 8, and then I simulate this so that the treatment group and control group are very different. And then I wrote. This is a simple case. Your linear model is good enough, but I also did Gaussian process and the BART. It's a very vanilla version. So you can see that what this is the result. It's very interesting is you can see linear. So this is the region where around 40, this is where I have most overlap. So you would imagine that you should have the least uncertainty. But then in this region and this region, this species is no overlap. So essentially, so no matter what your model is, so in reality, you have very little information to tell me about the treatment effect in this region and in that region. So then you should expect when you have a prior, your outcome model will tell you the uncertainty in these two regions should be big. So you can see that actually GP, so this is outcome, this is effect, I just separate this. You can see that GP actually achieves that. So Gaussian process has its own problem, but Gaussian process if you know a little bit about Gaussian process, it's kind of smoothing. It's like neighborhood smoothing. It's just keep smooth, smooth, smooth. And so when it realizes it doesn't have data here, it will just automatically increase the uncertainty. So let's see what the linear model does. Linear model also realize, oh, there's, realize, okay, there's not much data. The uncertainty increased a bit, but not too much, understood, but it's at least increased. But let's also look at BART. So let's look at BART. So what is BART? BART is basically a tree structure, right? So it's random forest, but let's think of it as a tree. So what does this kind of tree approach does is it assumes the same tree structure everywhere in the space, in the parameters, in the covariate space. So it doesn't matter. It cannot, because it's kind of the harsh thresholding in a sense. It just divides the space into those leaves or these rectangles. And so it assumes it doesn't really adaptively reflect the uncertainty according to the lack of overlap. So you can see what it does. Not surprising, like even though here it doesn't have much data, it still, it increases uncertainty, but just by not too much. So you can see the comparison of the average the treatment effect comparison. It's more or less, it's maybe like this. It's more or less the same. It doesn't really reflect the. So you can see the point estimate is around here is all the same, but then it's really, when you don't have data, you should have a large uncertainty. But you can see the BART cannot, just raw BART does not solve that problem. Okay. So again, this is a simple example. You asked me how do I evaluate that? Well, we don't, but I do know this is just illustrative example. Of course, BART people say that, this problem can be solved actually by use the Bayesian random forest, use 2 BART. It's better than that because again, that has divide the, there's a way of doing that. And another approach is called use the soft BART. That's where the some recent version of BART is a soft BART. Also, instead of doing this hard thresholding, it makes it softer so it can adaptively reflect the uncertainty. But the point of this example is really to show you that the Bayesian, so in high dimensional, in low dimensional, here, high dimensional really means the model is complex. So in Bayesian, it's important to choose a prior or some model that should accurately reflect the uncertainty for various degree of overlap. So try to avoid, again, I'm not saying BART is not good, because you can actually have a relatively simple fix, like use the Bayesian forest, then this problem is solved, or use a soft BART. But if you just use the vanilla BART, then you are having this kind of issue that cannot adaptively reflect the uncertainty according to the lack of overlap. And this is a problem very specific to causal inference, because overlap is such an important concept. So any questions about this example? So it's I got a lot of heat from the BART people say that you're making. I actually didn't. I just, this is the first simulation example I didn't cherry pick. I didn't do 1,000 ones, choose the one that really unfavored BART. It's just vanilla version, and then it doesn't work. Yeah, you can do some. So this is just showing them the danger of that. And then some people also use a differentiated process mixture, also get similar issue. But the key point is that Bayesian. The strength of Bayesian is to do uncertainty quantification. But uncertainty quantification should definitely, in causal setting, should include the uncertainty due to the lack of overlap. And then the choice of different priors is important, because that can have different properties in terms of its ability of reflecting that. So that's the first point. So the second point is also very interesting, pretty recent studies, several recent studies. It's called, so, there are different names of that, but it's someone called the regularization-inducing confounding. I don't particularly like the name because but the idea is pretty. So what it says that, remember, it was Bayesian, you use a spike and slap or regularization prior. The key thing is you're still doing regularize your model so that it reduce give the sparsity, right? So the idea, so they find, those authors find that with large P, the Bayesian regularization on the nuisance parameters in a causal model, like sometimes in causal inference we have like the primary estimand is the ATE, but there are a lot of nuisance parameters, and to do Bayesian, you have to have priors for basically everything. But then they noticed that sometimes seemingly innocuous priors actually will cause trouble, cause prior bias to that, and it's really this paper is a recent paper by Linaro, actually forthcoming JASA, very elegantly described this. So he was saying that, okay, so let's define something called selection bias. Well, also what is selection? This is unconditional X. Selection bias is basically the difference between the Y in the observed arm versus the potential outcome, the area potential outcome. And we know that without if you conditional X, then this 2 will be 0. If you unconditional, that's not. So that's called selection bias. So what the Linaro find is very interesting. It's so they find that remember earlier we mentioned that in Bayesian you make this assumption called prior independence. The propensity score model and the outcome model are a priori independent, the parameters, right? So this assumption is standard. So he actually found that in high dimensional case, so the standard Bayesian shrinkage priors. So there are many types of essentially the Bayesian high dimensional is all about shrinkage. So the standard Bayesian shrinkage priors for this models, for the prior and for the outcome model and propensity score model, they will lead to this guy a priori concentrate sharply around 0 as p increase. Okay, what does that mean? So you're saying that, well, Bayesian have often very standard priors to use like spike and slab, Bayesian non-parametric prior. But it turned out that actually if you are assuming this prior independence, which we take it for granted, what this assumption itself actually enforces the very strong information already in the analysis. So he find that he showed this example. It's like when your p is the number of parameters, is the number of the covariates. When p equals 1, this is the posterior concentration of this selection bias. So of course this is, this is pretty kind of a little bit. It's concentrated. It's a relatively flat around 0, right? But what is troublesome is as your p increase, as your number of parameters, number of covariates increase, this will just sharply concentrate around 0. So what does that mean? Basically say that if you have a high dimensional, if you have a lot of covariates, and you are using Bayesian, the standard Bayesian shrinkage priors, what you actually, and you are assuming the prior independence assumption that almost everyone assume, what you are doing is actually, as the covariates, number of covariates increase, the priors will so sharply concentrated around 0 that there's no hope even from the data you can recover, because it's so sharply associated, concentrated, because this prior independence assumption force the prior a priori to sharply concentrate around 0. Essentially, by default, you will actually get closer and closer to say that, oh, there's no selection bias. And this is actually a violation of the unconfoundedness. So this is called prior dogmatism. So this says that prior independence assumption, which looks almost like, well, this is just a standard innocuous, actually acts as informative prior, so strong that when the dimension is getting higher and higher, it will distort the analysis so much that it will be no hope to recover, even with more and more data, you will no hope to recover the underlying truths. So this later turned out to it's just a Bayesian analog of the Robbins-Ritov problem, the curse of dimensionality. There's a coda problem. So there's some deep theoretical connection to that. I don't think the paper actually was very clear about that. And when I was reviewing the paper, I realized, oh, this is the same thing, just a Bayesian version. This is again back to this Rubin's quote, say that any problems in one form of inference come up in the other form of inference. This is a kind of a Bayesian rediscovery of the Bayesian analog of the Robbins-Ritov curse of high dimensional problem. And again, after all of that, this authors say that, well, how do we solve that problem? Add the propensity score into the model. So it's very fun. It's very funny to see that all the smart people in the end doing Bayesian causal inference come back to the same conclusion. You have to add the propensity score into outcome model. Once you do that, this thing go away. Okay, so that is like there's no free lunch. You cannot, at the Bayesian, you cannot just bypass propensity score. So I feel that this is, to me, it's very, when I do this review, thinking about this, it's very it's very interesting philosophical, like going a loop and then back to the, to what kind of the frequency is not in the longest time. But Bayesian have additional benefit. So I think we're coming to the end. To summarize what we have learned is Bayesian causal inference. So yeah, it's a marriage. The marriage between the two is anything special. It's just Bayesian, and you're using Bayesian model for causal inference. So at least as I realize that there are a few things unique to this combination. First is the seemingly paradoxical role of propensity score. It's actually not paradox. It turned out that in the end, it's still, if you do causal inference, you have to look at the design, which is the assignment mechanism of propensity score, and the outcome, and you need both. So Bayesian is the same. Bayesian, there's no way Bayesian get around that. And second is, in high-dimensional settings, how Bayesian deal with all this outcome model is you see a shrinkage prior. And then shrinkage prior, they have issues also here. Remember, this is one thing. One interesting thing is, if you're a frequentist, you don't need this assumption. If you're a frequentist, because you don't have priors, so you never even need to assume the prior dependence. So this prior independence assumption is pretty unique to Bayesian, and that actually caused an interesting issue in high-dimensional regime. Is this is prior dogmatism or regularization-induced confounding. This is also pretty unique to the Bayesian causal inference, but there's also solution to that. It's, again, add the propensity score back. So another thing is overlap is still the king. The lack of overlap will cause a sensitive to the choice of the priors. Priors essentially is type of a model, and the outcome model. So this is the same in the frequentist domain, also in the Bayesian domain, which is just in the Bayesian domain that is reflect more in the sensitivity to the choice of the priors. And another issue I mentioned, the identifiability issue, it's a different concept now in Bayesian. So it's no longer zero all or none. It's a continuum between the weak and the strong identification. So those, at least I can see that is anything special. But of course, I didn't talk about, so I should hear. So why and when Bayesian? So it's funny that in my department, I never need to have these slides because everyone just do it. But in a general audience, I will say that, well, Bayesian is nice in many aspects, but Bayesian also comes with the price, the computational price. I mean, it's so I asked Donovan why people don't use Bayesian like until recent in causal inference. They say that, well, it's conceptually it's easy, but mathematically it's much more sophisticated